We will now apply what we've learned about rotational motion to kinetic energy. After dynamics and kinematics were covered, your physics education was continued with the concept of energy. Energy is hard to define, as we found out, but since it is a scalar quantity, it is very good for solving problems. So by now, hopefully you're ready for the concept of a rotational version of the translational kinetic energy. Given that kinetic energy is 1/2 mv squared, what substitution should be made into this equation to make it a rotational equation? We'll use the rotational equivalent of velocity, which is angular velocity, and substitute it into the kinetic energy equation. The first column here shows where you have one piece of a rotating object where the object is moving at velocity v, a linear velocity. And we now want to see what's its rotational energy as this object rotates. So we replace v with r omega, and right here, and you can see we're now using subscripts. This is just one small piece of the object, and it's the rotational energy of the object. So we have 1/2 mi times ri omega, the quantity squared. We square it, and we now have this term here for the rotational kinetic energy of one small piece of the object. Let's add all of them up. So we have here's piece 1, piece 2, then dot, 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 an infinite number of these pieces. And again, this is where calculus comes into play. We replace this with the common symbology of a sum, and this would be I to infinity of all these little pieces. And notice, why did we pull angular velocity out? Well, because it's constant, of course. For every single piece on a rigid rotating object, the angular velocity is the same. Then you recognize this term right here as the moment of inertia. So the rotational kinetic energy of an object, of a rotating object, is 1/2 I omega squared. You actually could have cheated a little bit and just started here and put in the rotational equivalent for mass, which is I, and the rotational equivalent for v, which is omega, but this just shows you a little bit of math and how we got there. The concept of work was introduced in parallel with energy, where work is equal to the force times the displacement that is parallel to the direction of the force, or anti-parallel, in which case you would get a negative. We're going to take a shortcut here to determine how much work is done by an applied torque. We're going to take the rotational equivalents of force and displacement, substitute them in this equation, and get work is equal to torque times the angular displacement. What fell out of this equation as we went to rotational motion, and why? Take a second to think about it. When you're ready, well, I'll go ahead and pull the screen down. You can pause if you'd like. Here we have a clear angular dependence. Down here we just have the product of torque and the angular displacement. The reason is torque is by definition, and this actually comes out of the vector math, is always perpendicular to the angular displacement. So in this case, sine theta always equals 1. And work will just be the product of the amplitudes. We don't have to put parallel or perpendicular here because they are perpendicular. So far in this course, we've discussed three types of energy: gravitational potential energy, kinetic energy, and elastic potential energy. All three of those were dealt with in terms of a point mass. There is no concept of rotation. We now have rigid rotating bodies, so kinetic energy will be redefined or expanded as a total kinetic energy right here that will equal translational kinetic energy and rotational kinetic energy. And we will abbreviate them capital T for total, little t for translational, and R for rotational. A common problem in rotational motion is having two different objects, each with the same mass and the same radius, and determining which will get to the bottom of an incline first. This is actually a great demonstration experiment. If they were just blocks or even spheres that slid down without rotating, they would get to the bottom at the same time. since objects fall at the same rate. By using an extended mass, not a point particle, rotation comes into play, and we'll get quite a different answer. Why is that? Think about energy, especially the kinetic energy we've been talking about. At the top of the ramp, both objects have the same energy. It's all gravitational potential energy. What about the bottom? For a non-rotating object, all of the gravitational potential energy that starts at the top of the incline is transferred into translational kinetic energy. And this would be for a block that's sliding down, or if you have a sphere and there's no friction, it just slides also. But if the object rotates, part of that energy goes into rotational kinetic energy. Rotational kinetic energy depends on the shape of the object, and that will affect the moment of inertia, which will then affect the acceleration. Let's take a problem. We have a sphere and a hoop. We have the same mass and radius, and they both start at rest at the top of a ramp. Assume that both objects roll without slipping. Which one gets to the bottom first, the bottom of the incline? As always, for starting physics problems, we like to draw a sketch. So here we have two inclined planes. We have a sphere that we're going to let go. It's going to go down this way, and a hoop that's going to go down this way. Typically in the lab, you have them both going down the same slope. But to make it look a little clearer as we solve the problem, we'll have different inclines. So what equation do we use, using the conservation of energy, that will give the velocity of the objects at the bottom of the ramp? Solve the equation. We'll actually go through that. Qualitatively, how can that be used to determine which object reaches the bottom first? Give a shot at this with your groups or on your own before going on to the next slide. We have no springs involved, so the only energy we're going to have is total kinetic energy, right here, and gravitational potential energy. This is the original at the top, and here's our final, which is at the bottom. We now put in for total kinetic energy translational and kinetic energy rotational, and we do that for both sides of the equation. Let's simplify it. At the top, up here, there's no movement, so all we have is gravitational potential energy. At the bottom, the height is 0. There is no gravitational potential energy, but we will have rotational and translational kinetic energy. We now substitute the values in here. We have mgh. They both have the same mass, 1/2 mv squared plus 1/2 I omega squared. This is the rotational kinetic energy. This equation right here works for both the hoop and the sphere. The only thing that will be different is this I when we start solving for the problem. The moments of inertia of those two objects are different. A little while back we mentioned that the sphere and the hoop are rolling without slipping. We made a clear distinction there between a box slipping down here without rotating, or even a sphere slipping down without rotating. Why did we do that? Well, if it's not slipping and it's rotating, we are allowed to use the equation V equals R omega. And we're going to get rid of this omega here by making this substitution, okay? If an object is sliding or slipping without rotating, or just rotating a little bit but still sliding and slipping, can we still use this equation? Well, pretty clearly not, but because that's why I'm asking it. But why? Think of a car on an icy road. When the driver hits the brakes quickly, what happens? The wheels will lock up, although anti-lock brakes help to minimize that, or rapid pumping of brakes for the older cars. You just push it in, take it out, push it in. You don't do that anymore. Anti-lock brakes do that for you. The car wheels will be slipping on the road, so instead of rotating nicely, they're sliding, just like this. The wheels don't rotate anymore, the car is just sliding. That is a very dangerous condition because you can't steer anymore. So the wheels will have a translational velocity. The car is still moving, but the angular velocity of the wheels, if they're not rotating at all, will equal 0. Clearly, V does not equal R omega in this case. Even if it's rotating just a little bit, the translational velocity will be greater than R omega. So we will now go back to the problem because we are assuming that it's rolling without slipping, so we can make the substitution omega equals V over R. I'm not going to go through each line of all this algebra here. I'd like you to do that on your own. I'll just point out the highlights. Here's the hoop, here's the sphere. Notice how we start with the same exact equations, and then we substitute in for the moments of inertia, which are different. Okay, here's the moment of inertia. And then we make that substitution we talked about where omega is V over R. Then you grind through some algebra, and you find for the hoop, the velocity of the hoop at the bottom of the incline is the square root of GH, and the velocity of the sphere is 1.2 times the square root of GH. The sphere has a greater velocity. The velocity of the sphere is 1.2 times as much the velocity of the hoop at the bottom of the incline. Did that surprise you? Qualitatively, that means that the sphere gets to the bottom of the ramp first, because at any point on the incline, the sphere has a greater velocity, where h, of course, is just the height above the ground here. Solving the kinematics equation for displacement would also give the same answer. One more question. Why did this happen? Both objects started with the same gravitational potential energy. And at the bottom of the ramp, both had zero gravitational potential energy and a maximum total kinetic energy. Both the same again. However, the hoop has a greater moment of inertia. More of its mass is further away from the axis of rotation, which is right in the middle of each of these objects. So there was less kinetic energy available for translational motion. It took a greater amount of the total kinetic energy to make it rotate. Hence, the sphere has a greater translational velocity than the hoop and reaches the bottom of the incline first.